So this is the last section of Chapter 4, and there are a couple of different probability concepts that we are actually going to cover in here. One of them being the probability of at least one. So we're going to show you basically how to tackle those types of problems in the last section here. And there's also, looking down a little bit further, this idea of conditional probability as well. So those are the two types of problems that you'll basically be encountering on the homework right there in the last section. And I am using the notes in Microsoft Word, so I'm editing a lot of the stuff in Microsoft Word. So if you are following along and filling these out at home, feel free to pause the video and stop it at any time if you need to write something in or go back over something that I've covered or whatnot. So first we're going to talk about the probability of at least one. Right here. And, when you're thinking about at least one of something, usually that's equivalent to the phrase like one or more of whatever, and if you're talking about in numbers, if you want to put it into context of values, you can say, this is like one or two of something or three of something or, 4, 5, 6, so on and so forth of something, okay? Now, on the other hand, let's think about what number is actually not involved in one or more, or, at least one. If you look at these values right here, the actual value that's missing from 1, 2, 3, 4, so on and so forth is the value of 0, okay? Or none of, the items of a certain type, or none. So, the ideas of at least one right here, this concept, and none, these are actually going to be complements of one another because, everything that's not at least one, well, it's none, it's 0. And these two ideas are going to be what you use, specifically probability of none is going to be what we use to actually find the probability of at least one. So it's kind of like a backwards kind of thinking, like we use the, you can think about maybe in some words the opposite, maybe. The complement, if you're thinking about it being the opposite, not necessarily the best way to think about the complement, but we're going to use the complement none to actually solve at least one problems. Now, understanding a little bit about like how to phrase things does help. You get to rephrase things a whole lot when you're dealing with these at least one problems. And the first few examples in the homework get you to think about like what are equivalent statements to some of the ones that they're given. And like in this problem right here, it talks about all being defective. Now, there's not any of those keywords right there, at least one or none. There's nothing in that all defective statement. So we got to figure out, is there a way that we can kind of incorporate maybe one of those words by maybe rewriting all defective. So what we're going to do here is we're going to take all defective and rewrite it. So think about, all defective. Well, that means, all of them are bad. Like everything has a defect to it. That means that none are good. You can say none are free of defects or none are good. Okay. Now we've worked in that phrase, none. So basically we're rewriting the word all defective to something that's equivalent to it. So we're making an equivalent statement. So if all of them are defective, that means every single one of them have a defect. That means there are none of them that are good. So these two ideas right here, all defective and none good, those are actually going to be the same thing. They mean the same exact thing. They're not opposites. They're the same. Now, we have this word none in here, and the reason I have that in there is now I can say, okay, if it's not none, well, what's kind of the complement of that? What's going to be, the rest of it? Well, it'll be everything that's 1, 2, 3, 4, 5, 6, 7, so on and so forth. It could, you could have 1 being good, 2 being good, 3 being good. That is at least 1 good. So one of the first things that you're going to actually be involved with doing is figuring out how do you incorporate this word like none or at least one. How do you incorporate those words into phrasing? Because you do have to rewrite things quite a bit when you are looking at the first few problems, because they usually don't have the words at least one, or they might not have the word at least one or none in the problem. So you have to figure out a way to kind of incorporate that. But this will be your answer right here. At least one good will actually end up being the complement of none are good. So I just took out that word none right there and replaced it with the word at least one. And that's how you make the complement. So now we know at least one and none are complements. Can we maybe make a relationship between those two probabilities where they equal 100%? Well, now since we know they're complements, we know that at least one of something, the probability of at least one and the probability of none, those have to add up to 100% if you're doing the percentages. If you're doing the the decimal numbers, it'll be equal to 1. So these two ideas, these two probabilities will add up to 100%, since we do know that at least one of something and none of something, the probabilities of those will actually, they're complements of each other. So we do know they'll add up to 100%. Okay. Now, a lot of times when we're doing problems, the reason we're going to do it this way, where we find probability of none, is because generally that is a lot easier to do than finding, one of something or two of something or three of something, so on and so forth. So generally the way we're going to find probability of at least one is find a probability of none, subtract that from 1, and that'll give us the probability of at least 1. And I kind of want to show you a justification for this, in kind of the way we did things way back at the very beginning of Chapter 4. It may seem complicated to find the probability of at least one using this formula. So we're going to justify this with the reasoning below. We're going to say, okay, let's let this space be, having 3 births, and you're looking at like the biological, gender or whatever they assign the babies at birth. So we're going to say we have 3 boys born first. We'll say all 3 babies are boys. And then you could have, what are some other things that could happen? Well, we could have 2 boys and the last baby is a girl. We could have a boy, a middle girl, and then a boy. Or we could have a girl first and then 2 boys. That's all the ways you can get 1 girl and 2 boys in 3 births. You could also have it be where you have 2 girls. So 2 girls can happen on the end. 2 girls can happen, on the outsides. Maybe there's a boy in the middle. And then you could also have a boy or a girls first and then a boy. And then the very last option right here, you have all girls. So these are all the possibilities right here. You can see there's 8 different possibilities right here. Now, when you're looking for at least 1 boy, well, look at all the things you have to kind of consider or look at for at least 1 boy, okay? And you can find the probability by listing it out like this, but you're going to see, like, this is not going to be the preferred way to do it. But if we're looking right here, at least 1 boy, well, that means 1 boy. So these 3 options right here, 2 boys. So it could be these 3 options, or 3 boys. At least 1 boy means 1 or more boys, okay? So you would see that there are 7 different options here out of 8 total possibilities. So that would end up being your probability of at least 1 right here. 7 over 8. So we see that if we do probability of at least 1 boy, like we're trying to find this probability here, we're going to see that we end up getting 7 out of 8 different possibilities for that. And, the way we want to do it, if you look here, how many of these did we end up not counting? Well, actually, if you look at this, we only ended up not including this one last possibility, the one where it's all girls. So there's only one possibility where there were none of them being a boy. This is a lot easier usually to count than all the possibilities where at least 1 happens. At least 1 can happen so many different ways, but none can only happen 1 way. And this is actually going to end up being the way we want to process these kinds of problems. So look at it this way. What is the probability of no boys? Well, we said that there was 1 out of the 8 possibilities where that could happen. None occurred only 1 time. So way we could do this, if we were trying to find at least one, and this is the way you'll probably be using for the most part from here on out. If you want to find the probability of at least one, we're basically saying, okay, well, let's find the probability of none of that happening. And once we find that probability, which means we all had girls, probably of having a girl is like 1/2 chance of that happening. So, or 0.5, you can say that 0.5 chance of that happening. So 50%, okay? We know that probably having a girl is 50%, and we want all girls since we don't want any boys. Well, that's 0.5, 0.5, 0.5 right there, okay? That'll end up being 1/8 when you multiply it, so you'll get a 0.125 right there. And when you subtract this out, that's where you'll have your ending result, 8.75. And if you look at the decimal here, 7/8 is the same exact fraction we got doing it this way versus the other way. Now, there might be a lot more multiplication or whatever in this method right here, but you won't have to list out all the possibilities doing it this way like we did up there. So you don't really have to even have the list. You can actually just process it like this. So this is going to be the way we want to do at least one. Kind of going forward is use this idea of, okay, let's find none first, then after that we'll subtract that from 1 to get at least one. So you can talk about the percentage here. It's an 87.5% chance of at least one girl at least one boy in 3 births. That's what we ended up finding. Okay, as our final answer there. Now let's look at another problem down here. The FICO score is commonly used as a credit rating score. There is a 1% delinquency rate amongst credit users or consumers who have FICO scores above 800. Okay, and then we want to pick 4 consumers at random that have a scores above 800. Find the probability that at least one of those 4 become delinquent. So, if you're thinking about all the possibilities for one person to be delinquent, well, you could have your first person be delinquent. You could have, your second one, your third one, or your fourth one. Or you could have 2 of them, or you could have 3 of them, or all 4 of them could be delinquent. So there's a lot of different ways you can have 4, when you have 4 people, you can have at least one be delinquent. There's a lot of different ways that can happen. So here's what we're going to be doing right here. What we're going to do is first assume that, these are going to be independent events. We are going to assume that picking 4 people out of however many people there are with FICO scores above 800, we are going to pretend that is less than 5% of the total. It's probably safe to assume that, honestly. So yeah, 4 people out of probably the thousands of people is probably going to be less than 5% of the population. So these are going to be treated as independent events, so we won't have to worry about changing our probabilities as we multiply when we use the multiplication rule. So what we're going to go down here is, we know the information that they gave us was the probability of a delinquent. We see that that's a 1% chance. So, well, what does that also give us? Well, if we want to find the probability of somebody that is not delinquent, that's going to be your other 99% chance right there, or 0.99. Okay. Now, we want to find the probability of at least one of the 4 being delinquent. Well, the easiest way for us to find probability of at least one is to find none being delinquent. So we want to find none first. There's only one way that can happen, and then after we find this probability here, we can actually subtract that from 1. So the probability of having a not delinquent person, from picking the people out of with credit scores over 800, well, we saw in the problem statement it gave us a 1% as delinquent. That means 99% is going to be our not delinquent. So the probability of the first one not being delinquent is 0.99. Now we don't have to worry about, since we are saying these are independent, the selection of each person is independent. That means the second person also is going to have a 0.99 chance of being not delinquent. Then your third person, we want 4 non-delinquents, right? So we want none, we basically want none of the 4 to be delinquent. So that means not delinquent, not delinquent, not delinquent, not delinquent. So we're going to have 0.99 right here as well. And then we'll also have a 0.99 over here. So then you'll go ahead and multiply those out right there. Definitely good to have a little calculator for this kind of multiplication for sure. We have 0.99 multiplied by itself 4 times. So I just need to raise 0.99 to the 4th power. And then I want to subtract that from 1. So that's basically probably of none of the 4 being delinquent. So it's a 0.9605 chance or whatever. Then we want to subtract that from 1. Oops, go back here. Subtract. Alright, actually I want to do 1 minus the answer. 1 minus the answer. Get my calculator stuff fixed up here. So it looks like we have a 0.0394 chance. So 0.0394 chance, or you can say 3.94% chance. 3.94% chance of what? So what were we ultimately trying to find? Well, it's a 3.94% chance at least one of the 4 people chosen are delinquent. So basically we first found the chance of none of them being delinquent. We first found that. Then all we did was we subtracted that probability from 1, and that's how we get at least 1. Okay, because there's only one way you can have none of them happen, and then everything else is going to be 1 or 2 or 3 or 4, which is at least 1. So this is the easiest way to find your at least 1 probabilities. Okay, right here. We'll do one more problem with at least 1. Now this down here talks about the principle of redundancy, and this is kind of a common, I guess, principle used in factories and places where you have components that basically keep your system going. It improves your system reliability because you have multiple components that do the exact same job together. Okay, so this one says assume your alarm clock. We're using alarm clocks in this example. Assume that your alarm clock has a 0.86 or 86% chance of working on a given morning. So basically you have an 86% chance to wake up each morning. And this says, we'll answer these following questions. The first question says, what is the probability that your alarm clock will not work on a given morning? So we do know that in the problem statement it gives us the probability of working is 86% or 0.86. You could say it like that. So this means that the probability of not working, well, that's going to be the rest of whatever you need to get to 100%. So that'll be 1 minus 0.86 right there. That'll be your 0.14 or 14% if you want to talk about in percents chance of not working. So I'll highlight this in blue as my answer for that first part right there. There's what you want to have as your answer. Okay, so that's the probability the alarm clock will not work on a given morning. Okay, let's say you have 2 alarm clocks on part 2. What is the probability that they both fail on the morning of some kind of exam? Okay, well, what you're going to do here, so you want to do probability that none work. So you basically are saying like the first one don't work and the second one don't work. So like it's basically probability of don't work and don't work. So we know that since we have that and keyword, we are going to end up multiplying for this problem. So we want 0.14. They are the same type of alarm clock, and we are going to assume they're independent. So like we'll assume one of them is maybe like your phone, and one of them would be your wall clock or outlet clock or something. You would want them to have independence, since you wouldn't want them to connect to the same thing because they both could fail. So we're going to assume they have their own battery packs or their own method of working. So the first one is 0.14. The second one will also be 0.14. So now we can multiply these two right here together and see what this is going to end up being right here. 0.14 squared, 0.0196. if you're doing that in percentage, like it's basically a 1.9% chance none or neither of them work. Okay. Now, it says with one alarm clock you have a 0.86 probability of waking up, okay, or being awakened. What is the probability of being awakened if you have 2 alarm clocks? Well, if you're wanting to wake up with 2 alarm clocks, okay, so let's say probability of waking up. Well, what happened to make you wake up? Well, one of the alarm clocks worked, like one or the other, or both of them worked. Those are the situations that cause you to wake up. So your first one worked, your second one maybe didn't, or your second one worked and your first one didn't, or both of them worked. That's the probability of at least one works. Okay? And since we already have the probability of none working up here, like we found it in part 1, just right up, or part 2, just right up here above, that's the probability of none of them working. Well, all we need to do is say, okay, 1, take away the probability of none. After we do this calculation, that will give us at least 1. So if we do 1 minus none, that'll give us at least 1. So we're using that same formula again with this type of problem. 1 minus, I think I still have that answer in there. It'll be 0.9804. So you can say 98.04% chance. You can say at least 1 works. Or you can even say like 98.04% chance to wake up. Both are the same thing. But this is basically what you found just now. Okay. And, you did improve your reliability. With one alarm clock, you had a 86% chance to wake up. Now with 2, you have 98%. You did definitely increase your overall reliability on your system of waking up in this case. So yeah, you did improve it. You could still have malfunction, but now it's definitely unlikely that you're probably not going to wake up. You've lowered it below 5% chance of not waking up. So you definitely improved your overall reliability. Okay, and that's basically how you're going to do the at least one problems on the homework. You want to basically go in and figure out first. You might want to reword problems. You always want to kind of reword. Like this problem right here gives you a great example of how to reword stuff. This one talks about being awakened right here. Well, I had to think about. What does that even mean? Like, what does waking up entail? Well, that means at least one of my clocks worked. So I kind of had to work in that phrase, at least one. And that's what I was talking about earlier. A lot of times you end up having to reword certain, phrases so that so you know how to work with the problem. But that's what you're going to be doing on some of these problems is after to find at least one. Well, a lot of times it's easy to find none. You'll go over here and find probability of none of something happening, and then you'll subtract that from 1 because there's only one way that none can happen. Both things don't work. For 2 alarm clocks, like the first one don't work and the second one don't work. That's only one possibility, if you're looking at listing it out or whatever for your possibilities, but that's what you're looking at. So the only other thing we need to talk about now is conditional probability. And there is one thing about conditional probability that makes it a little different from every single probability problem that we've kind of covered in the chapter up until now. So we'll show you what that is when we get to the problems. But conditional probability is the event that probability obtained when you have some other piece of information already occurring. I kind of call this like your given information, like you already know this happened or whatever, like it's knowledge that you have gained. But you'll see like this notation right here for conditional probability. It's a little bit different from stuff we've already seen. There's no like and or word. It's got this like bar in the middle of your probability statement. The way you read this is it's the probability of event B occurring given that event A has already occurred. Okay? So we're going to show you basically how you're going to be arriving at this with, a problem down below. And then maybe we'll come back and talk about, how do you calculate conditional probability right here? Like going through like basically what I'm going to be doing to find these kinds of problems, the solution to these types of problems right here. But basically what I'm going to do is, one thing that's good you're going to notice when I do the problems is, because you're given information about some other event, like you're given A, this is actually going to give us a denominator that's different from, it's not going to be the total of the whole table, or it's not going to be the overall total. And you're going to see why that is in just a second. Okay? So we're going to go down to a very familiar table that we've seen before. This is our little lie detector test results that we used earlier. I like these kinds of tables because you have all of your information right here to you, so you don't have to worry about going somewhere else and getting information. But this problem right here, it asks us to find the probability of a negative test, and then there's that bar given. That's the way you read it, is like given. So it's like negative test given. I can't write this. I'm trying to write with my mouse, so enjoy that. Given. So negative test given that the subject didn't lie. That's basically what we're ultimately trying to find with this problem right here. Well, because we know the subject didn't lie, like we're given the subject didn't lie, we're actually only going to look at those people. Those are the only people that we are interested in. Because if we're given, or if we know already occurred, like the subject didn't lie, if we already know that, well, we would not be interested in lie people. So these people aren't even in the consideration for this problem right here. So what does that mean for us? That means you're going to have a new denominator. That part that's behind the bar is actually going to give you your new denominator that you work with. In this case, it'll be 42, okay, that we use for our denominator down there, okay? And then, how do you find the actual answer? Like, how do you find the top number, the numerator? Well, how many people of those left over will have a negative test? Well, the only ones that have a negative test are the 30 out of, and then the 42 is our new total. And that's going to be our conditional probability right there. And you definitely want to simplify that as much as you can. I'm just going to simplify the fraction. Well, I'll make it a decimal right quick with my calculator. 30 over 42. Sorry. 30 over 42. 0.71. We'll just do 3 decimal places. 0.714. But that's basically how you're going to do these problems that involve the conditional probabilities. The little bar, or whatever you want to call it right there. Okay? The given bar. But that's essentially what you're going to do. So right here, what we're really wanting to find is probably somebody with a negative test, given that we know they didn't lie. That's basically what we did right there. We looked at those that didn't lie, and basically this gave us the total amount of subjects in the table. In the beginning, there's 85 total, but for conditional probability, we cut this down. You cut down the total, so we have like a new total that we're going to be working with right here. So we cut down this total since we were given information that the subject didn't lie. This narrows our total people we're selecting down to just 42. So this is what I call the new total whenever I'm doing these problems, the new total. Then among these 42 subjects, we saw that 30 of them ended up having a negative test. So this is the explanation basically of what we just did right here. But that's what you're going to be doing when you do these problems. So like a good practice would be, before you just pause in the video right now, would be awesome, I think, and just seeing if you can do these two. I'm definitely going to fill them out myself, but just to see if you yourself can you figure them out. These are actually some of my once you get the idea or the way to do these problems, I feel like these are some of the easiest ones in the whole chapter to do once you get that rhythm down. But yeah, you definitely have to go through them and try some out first so you get a feel for them. But let's look at this first one, B, right here. Okay, so this one wants us to find the probability of a subject who didn't lie, given that they got a negative test right here. Okay, so what we're going to do, I'm going to go back up here to my chart. I'm just going to get rid of these. We're given that they had a negative test. So this right here is kind of like my new total. So I want to use this negative test results right here. This is going to be my new total. So negative test is going to be 30 and 6. That means I'm not even going to look at anybody who would have a positive test. Those people are canceled out for the rest of the problem. The only people, since I'm given information, only people I would look at are these two right here, these 36 total people. Okay, so that kind of gives you your new total. And now what we want to see is, okay, from those that are left over, how many of those didn't actually end up lying? Okay, the didn't lie category is down on this first column right here. So this is the didn't lie category. Looks like we have 30 people did not lie. Okay, remember the 12 is already canceled out from above, so the only ones left is that 30 right there. We have 30 people that did not lie. And then you'll just simplify that fraction right there. Okay, I'm just going to simplify it by dividing the common factors actually. So that's 10 over 12, which ends up being 5 over 6. I guess that's good enough. That's going to be my answer. Okay, look at the next one here. Okay, this one is lied given a positive test. Okay, so positive test is going to be kind of our new total. It's the part that we're given. So if we're given, we know that they have a positive test. So what we're going to do, let me erase my from my last problem. We're kind of resetting it. Okay, if we're given that they had a positive test, we're only going to be looking at 12 and 37. So 30 and 6 are basically eliminated right there. Okay, then that's the positive test, people. That's our new total. So we have 12 and 37. That's 49 is going to be our new total. Now we want to say, okay, of those 49 that are left, how many ended up lying? Well, we see that there's going to be 37 that lied. So this will be 37 over 49. And you can reduce that to a fraction or a decimal, whatever is needed. Okay. What about doing it doing these the other way? What if we swap the order of these bars? Well, positive test given that they lied right here. Well, lied. Let me erase my last stuff right here. If they lied, it's going to be these two right here. So these two right here, 12 and 30, since they told the truth, they're actually gone. So since I'm given that the person lied, this would be like my new total right here, 37 and 6 right there. Okay, that's going to be 43 total. So I have 43 people who lied. Now, how many of those 43 had a positive test? Well, go back up here. Positive test is the bottom, the first row. So it's going to be 37 people who lied or who had a positive test, given if they're a liar. Okay, so 37 out of 43. And that's probably the way I do those kind of problems. That's the way I think is the easiest right here for those types of problems. So you can try those. I think those, definitely once you get the hang of those actually end up going a lot quicker than some of the other problems do right there. But obviously, if you have any questions, you are free to text me as you're working through the problems in 4.3. They're definitely, I definitely say the harder part of the homework is going to be doing the at least one section. I think it definitely it requires a lot more thinking because you do have to reword some things a lot of times to incorporate either that word at least one or the word none, in that case, like one of those two. And that's your main goal, is to get that wording in there. Then you're able to figure out, okay, how am I going to solve this? Generally, none is not too bad to solve if you're having to do it. But the at least one, that's where you have to say, okay, well, there's a lot of ways that can happen. Let me go ahead and figure out none and then subtract that from one first. So hopefully if you have any questions, though, you'll text me and remind and whatnot. But yes, good luck as y'all are going through your homework this week.